So now we move on with more rotational kinetic energy and a problem that's a little more complex. So in this case, you can see we've got mass 1, mass 2, and a pulley and a line here that will be discounted and some forces going on. So two blocks with masses 5 kilograms and 7 kilograms are attached to a string over a pulley with a mass of 2 kilograms. So the pulley has is going to have some inertia relations there. The pulley, which turns on a frictionless axle, is a hollow cylinder, so there's your geometry, with a radius of 5/100ths of a meter, over which the string moves without slipping. Okay, another clue. The horizontal surface has a coefficient of kinetic friction, we're back to friction, of 0.35 or 35/100ths. Again, remember, coefficient of kinetic friction has no units, so it's just a number. Becomes a multiplier. So let's find the speed of the system when the block of mass 2 is dropped 2 meters. Okay, so this is going to be the driver of everything that happens in this problem. That's our mover. So potential energy is going to equal the potential energy of gravity. And which one is that going to be? That's going to be mass 2. So we look at the non-conservative work component. The non-conservative work component says we're going to look at the change in kinetic energy tangential, and the change in kinetic energy rotational, and the change in potential energy gravitational. So those are our terms for our non-conservative. Can we boil them down a little bit? Well, work non-conservative, if we deal with that term of friction, the coefficient of kinetic friction will come into play in one of these values. So minus mu k times the normal times the change in the distance. It's marked as x, but it's going to be in the y-axis. Mu k, then m1g is replaced for n and delta x. So moving forward then, mu k n delta x then will equal mu k mass 1 gravity delta x is equal to 1/2 mv squared, where that we're talking about mass 1, plus 1/2 mv squared mass 2 minus 0, in both cases minus 0, and 1/2 I omega squared minus 0 plus 0 minus mass gravity height. Okay, so we've brought in all of our initials in, and what we have left is our finals. So in this case, as I said, the delta x that mass 2 moves through is going to equal the height. So it will also move mass 1, but this is where we need it. So since we're dealing with a hollow cylinder as our pulley, we use our specific relationship. I is equal to I by r squared over r squared here, so that we end up with minus mu k mass 1 gravity times height is equal to 1/2 mv squared plus 1/2 mv squared plus 1/2 I over r squared times r squared omega squared minus m2 gh. Okay, so we're going to use the relationship. Again, I is equal to mass times the radius squared for the pulley. So m in this case is going to equal I over r squared. So the velocity then equal to the rotational velocity r omega, so that v squared r squared omega squared becomes a value then that we can use for substitution. Mass 2, the gravitational height, okay, that's going to be our potential energy for the box, the mass 2 block, minus mu k m1g h is going to be the friction component associated with mass 1, but it certainly plays on mass 2, is equal to 1/2 mass 1 velocity squared plus 1/2 mass 2 velocity squared plus 1/2 mass 2 velocity squared. So all we're doing here is we're going through and we're rearranging terms and simplifying our terms here so that we can make things easier. Okay. So what we end up with then is we're going to factor out 1/2 out of each of those terms, and we're left then with mass 1, mass 2, mass 3, okay? And we're going to factor out the velocity too, because the velocity is going to be the velocity for every one of these components. So solving for velocity squared, then velocity squared is equal to 2 times the gravity times the height, because we're going to factor this into the numerator over here. Mass 2 minus mu k1, and we're going to divide that by the sum of all of the masses. So the velocity then overall equals that term. We put in our values, 2 times the gravity, 9.8 meters per second squared, 2 meters that the box moves in the y direction, 7 kilograms, 0.35, and 5 kilograms times 0.35 when we add our frictional component in and the sum. So sum all these up in your calculator, and we will get a velocity of 3.83 meters per second. So you can see we have to look at each one of our components and determine how it reacts with respect to energy. Angular momentum. All right, so let's do a little more defining here. We know that if we sum all of the torques, we come up with the momentum, or the moment times the acceleration, rotational, and that value of acceleration, rotational, is the difference in omega final minus omega initial divided by delta t. So now we have a relationship then that we can use to develop some expressions to help us solve for the problems. So the angular momentum is defined as L equal to I omega. So going back to our definition of defining what we've shown above, the change in angular momentum then will equal to the time interval. So there's our angular momentum, there's our time interval. So it comes out to the summation of the torques. Can also be used and solving for the change delta L over delta T. The torque acting on an object is equal to the time rate of change of the object's angular momentum. So now we're back to momentum. This is analogous to Newton's second law, where we saw the force is equal to the change in momentum over an interval of time. So here's an interesting little problem. We've got a guy sitting on a pivotal stool. He's got some weights in his arms, and he's going to bring the arms in and out, the weights in and out, and we're going to see how it affects the velocity angular. A student sits on a pivotal stool while holding a pair of weights. The stool is free to rotate about a vertical axis with negligible friction. The moment of inertia of the student, weights, and stool is 2.25 kilogram meters squared. The student is set in rotation with arms outstretched. So he starts with his arms out, making one complete turn every 1.26 seconds, arms outstretched. They want us to solve for the initial angular speed, omega, of the system. Find the initial angular speed. So we can say that omega initial, since we're dealing with a rotation, is 2 pi times the frequency. Well, frequency is a per unit of time relationship. So we can substitute 1 over time for frequency, and we have 2 pi divided by time. And typically a big T means a period. It happens once, it happens twice, it goes on and on and on. So in this case, it takes 1.2 seconds to make one complete revolution. So we have 1.2 seconds divided into 2 pi gives us almost 5 radians per second. Notice we have changed now to radians. Okay, as he rotates, now he pulls the weights inward so that the new moment of inertia of the system, that's the student, weights, and stool, becomes 1.8 kilogram meters squared. What's the new angular speed of the system? So we go back to the definition saying that we can solve for L initial, which is equal to L final, and then stretch it out. We can expand that then to I initial omega initial is equal to I final omega final. I initial was 2.25 kilogram meters squared. I final was 1.8 kilogram meters squared. Okay, both of these were given in the problem. And we just solved for the angular velocity, almost 5 radians per second. So 2.25 kilogram meters squared, almost 5 radians per second. When I multiply those together, then I will come up with a value then of kilogram meters squared per second. And set that equal to the final 1.8 kilogram meters squared times omega final. Okay, we're going to solve for omega final. What happens when we pull those weights in? So we get 2.25 kilogram meters squared times 4.99 radians per second. And we're going to divide that by 1.8 kilogram meters squared. So our kilogram meters squared disappear, and we're left with a unit of radians per second, 6.24 radians per second. Now they want us to find the work done by the student on the system while pulling in the weights. Ignore energy loss through dissipation in his muscles. Okay, so there's things that you can certainly build in. Friction, air resistance. Now they're saying ignore the dissipation of the energy lost in his muscles. So the work done by the student then is equal to the change in kinetic energy rotational, 1/2 initial, final, minus 1/2 initial in both of these terms. So we drop in our values, 1.8, 6.24, 2.25, 4.99, and we come up with the work done by the student of 3504.04 kilogram meters squared per second squared minus 28.01 kilogram meters squared per second squared. We know that kilogram meters squared per second squared is our energy or joule relationship. So when we take the difference in those two, we end up with the work done by the student, 7.303 kilogram meters squared per second squared, or 7.03 joules of energy, the work done by the student on the system by pulling in the weights. So that wraps up our rotationals stuff, and now we change gears. Things start to look a little different now. Some of the information we're going to use again, but now we're going to use it for solids and fluids. For this section, I have included lots of practice problems. Make sure you look at the videos and the practice problems for this chapter.